In the next subsection, we'll look at suffix trees, which will turn out to be a versatile and really useful data structure that's very easy to define, but hard to compute. And I called it a magic data structure here because very smart people essentially thought it's not possible at some point. And to motivate that, here's an exemplary problem that we will come back to as well. It's called the longest common substring problem. You're given a collection of strings, k strings S1 up to Sk. There's some example with 2 strings, but it can be more. And we want to find the longest substring that occurs in all of these strings. So it's somehow a pattern that occurs in all of the strings at some point, at some location. And the longest such, please. So for these two, the second is not too long, so you can try to figure this out. It turns out to be alive that occurs here and here. And don't get tricked by this being different strings put together. So the question is, if you just have 2, maybe you get around with just trying different options. If you have k strings, it sounds like this is even tougher. And the question is, can we do this by basically reading every string just once? That's what this time would be. It's the time to process all characters. You can take a constant factor more, but that's all you're allowed. Should that be possible? It sounds like it sounds unlikely because it feels like you have to test all possible combinations of positions, or at least all possible substrings, and check if they occur or something like that. And it turns out that the suffix trees are able to solve it in that time. And if you haven't seen it before but thought about this problem for a while, it feels like this is not possible. So suffix trees are a way to do full text search in strings. They're linear time and space. So in a time and space to just look at the string once, you can build this. And you can solve this problem and many other problems in almost best possible ways usually. And to further give credit, to give evidence for this, there's a quote from a textbook on suffix trees and other related problems that says Don Knuth, that's the same Knuth from the Knuth-Morris-Pratt algorithm, and well, famous for his books, The Art of Computer Programming, also the creator of the TeX typesetting system, and in a way, a central figure in theoretical computer science for sure. So a while ago, but yeah, so he thought about this problem as well and said, no, it sounds like this is not doable. But he was proven wrong, which, if you look at it from today, is awkward because it sounds so easy to do with the building blocks we'll look at. So in 2 weeks' time, you will know how to do it. But there's a few conceptual jumps in between that were really hard for people to take. Luckily, they're much easier to understand once people already know what to do. It's one of these cases where inventing something is harder than understanding it once the invention is out. So what is a suffix tree? The suffix tree is defined for a text, and we'll always add this $sign. So same convention as before, but we have a single string, a single text, but we add this $sign at the end, which will just turn out to be convenient. And what we built is a compact trie, what you've just seen, and of what set of strings? All suffixes of this extended text. So you immediately see why the $sign is useful there. It means that this set of all suffixes is prefix free, which was what we needed. That's the definition. Let's see some example. So here's a text, banana ban, with $1 added. these are all the suffixes. So you just take the whole thing, delete the first character, delete the first two, the first three, and so on, all the way down. And you build a compact trie. So I've just drawn this sideways so that we can write the labels of the leaves nicer. Here's a conceptual view of the compact trie that we'll sometimes use because it's a bit more human-friendly, where I wrote the entire string as the label on the edge. Remember from before, compact tries, they contract these sequences of unary nodes, and then they actually just take the first label and represent in the internal nodes how many characters did I skip. But we can conceptually write this by writing the full label on the labels. We know that in reality, this is what it looks like in, okay, there's one more before that, but I'll come to that. In the computer, it's stored like this. We have the offsets in the internal nodes and just the first label on each edge. That's the compact trie part, but it's convenient to write it like this for us to reason about. The second change is, if you look at this, it looks like it's storing this parts of this same text over and over again. That's of course not necessary. You can store the text once and instead store in the leaves only the starting position of the suffix. That's enough. Then you know suffix 4 is everything starting at 4, so it's this naban. That's what it was. So a suffix tree is that, a compact trie of all the suffixes of the text, but in the leaves we store the starting index, not the full string. Okay? There's also these three representations that we'll jump between. This one, where the internal nodes have the numbers and just the first label is on the edge, that's the computer representation, the one that one would want to implement to not waste space. This is the version that we'll usually work with because it's easier for us to reason about with these edge labels here. And okay, the first one, the third representation, is where we spell this out. Sometimes I'll also use that. Questions on the definition? One thing I should say about tries, I haven't pointed this out in the previous section. If you have a set of strings or a set of suffixes in this case, you can insert them one after the other in a trie, and the resulting trie doesn't change if you change the order of insertions. That's very different from the binary search trees, where you remember if we had the sorted order, it would be this completely degenerate case, and if you balance it more, then it would be nicely balanced. Not for tries. In tries, the structure is completely dictated by the strings, and so the order of insertions doesn't matter. That's one convenient bit. And so it means we can say we just have one specific trie. The suffix tree in this case is well defined for just the string. You don't have to ask what's the order of insertion or anything like that. So that's all the magic there is in the suffix tree. We'll come back to how to solve this cool problem that people thought is not possible in this fast time with suffix trees. The tough bit about suffix trees is how to construct them quickly. And let's have a look at how to construct them slowly, but simple. If we have a text of length n, so n characters, it actually has n+1 after we added the end of word character. Then we can build this suffix tree in the simple route is take each suffix, insert it into a trie, and at the end you have the suffix tree. So you could, the most straightforward way to do it is to build the non-compact trie first, then compact it, and then replace in the leaves all those pointers, all the strings by just the starting index. The problem is that this takes essentially quadratic time because the first half of the suffixes, they all have at least n-half characters, and you always have to traverse the trie. So that alone already takes quadratic time, even if you're not starting with a standard trie. So that doesn't work. And for now, we'll just leave it as a magic black box. The amazing result that we'll eventually come back to is you can construct a suffix tree in linear time. You're given the string, and there's a magic procedure that spits out this thing without going through a lot of effort. It's a little tricky to go into the details, but we'll build up to this. And this was the part that was not clear if it's possible. Because this construction, taking all the suffixes and building a trie on that, that's straightforward enough for researchers to come up with before the time. But whether you can build it quickly, that was the part that wasn't clear. And so that's the big box to look out for. For the moment, we'll just take that for granted and see what we can do with it. But we'll come back to it. Now, because many of you haven't seen tries before, I wonder if it's useful if we construct this trie from scratch to see how you come to this. Essentially to reinforce the definitions of tries, etc. So this is not specifically about suffix trees, really, but to give you a feeling how to do that. Banana ban. Okay, I probably want the indices, but let's try. So we'll start with the standard trie because these are easier to construct for humans. And so again, the procedure I'm showing you now, that's the crappy slow algorithm. That's not what we want to use at the end, but it's the one that is easier to follow. So we start by just inserting the whole string. So I'll need a lot of space for that. Let's try to be small. Nah. Okay, I'll first write banan. Nah. Okay, I can make it a bit bigger, right? It's a bit extreme. Can't see much. Ben. Okay, now I'm used up a bit too much space here. It will probably be taller than white. So let's see. And we need the dollar. Okay, this will be messy at the end. That's one string inserted. Now let's do another one. Let's do the one that starts with an A. So ananaban. That's going down this route with A. And nah. Ben and the dollar. And then we have another leaf. I'm leaving out the contents of the leaves, but what should go there is 0 and then 1. So that's already the indices where we started. So the next one is nanaban. That's again another link from the root. So that was B. N, nah, nah, ban, and the dollar. It's really tedious, but it gets faster because the strings become shorter. And now the first time something interesting happens, if we start with this one, we have anaban, which reuses parts we've already built. We do A, N, A, but then comes ban. That's an N. And the dollar. 3. Okay, now naban goes down this path, N, A, and then we fall off with ban. There's nothing more educative than doing a quadratic algorithm by hand and suffering real hard. Shows you much more why you don't want to use them. So we've done naban, next is aban. So we go down here and then we fall off with ban. It also shows you that there's some pattern. That is 5. There's always this ban at the end that seems to fall out of the tree. Now here's another one, just ban. This is actually in the tree, but we fall off with just the dollar. Then N would go here and then fall off with the dollar. Is that 7? And just N fall off with the dollar. And well, just the dollar if we want. Falls off right at the top. Oof, that's the standard try. Now we have to contract that to get the compact one. Fortunately, that's not quite as bad. And I'm drawing the human version, so we don't have to figure out the indices. So we have 1, 2, 3, 4 children at the root. Let's try to draw that a bit neater. And so we can do A, B, N, dollar. Sort them alphabetically while we're at it. Now let's take the A branch. There's 2 children. One that needs a lot of space with an A. And the other is just ban dollar. So that will all be contracted into one edge. Okay, I'm writing very small now. Then let's continue like a depth first search. AA brings us, sorry, that's an N, right? That was an N. I read it as an A. AN brings us down here. And then that has another 2 children, A and dollar. And here we continue. We have 2 children, one with N, one with B. The B is just one long chain, so we can directly write ban dollar on the edge and go to leave 3. And the other one is actually also one long chain. I'll need more space on that edge because it's naban dollar and it goes to 1. Okay, you see how this goes? Shall we continue the rest? I'll try to speed up a little. So we go B, that's actually a whole ban. So we're down here. Fall off with a dollar for 6, and then we have a one long anaban. And the dollar. That was the whole string. Then for the N branch, 2 children again, one with A, one with dollar, and that falls off right away. And this one branches out another time into N and B. So I'm at N, A, N, A. B goes down to ban. No node. Just one long edge. That was this one, 4. And the other one is also one long edge going down to Naban. And the dollar. And 2. And that's it. So you both see in this example that it's painful to do the full thing. It's also visible that it has much less nodes, this compact trie. And apart from the human-based version that we write all the strings on the edges, that's the suffix tree. Okay? So it's not too hard to construct these manually. It's just tedious, but that's the slow algorithm. We don't get the magic results from using that one. That doesn't scale with large strings. Good. So just assuming that this fast construction does exist, what can we do with it before we bother to learn about it more? I have a fairly mean summary question that's trying to test you on your understanding of this definition. Okay, I'd love to start it. There you go. It's basically just to have that fresh in mind before we use it. Interesting even split. I'll wait for a few more people. Let's do 35. One more. Okay. So let's see. We have some votes for most things. There's also many correct answers. Let me briefly recap. So we always put $sign at the end of t. That's correct. The size of the suffix tree is never quadratic. It's always linear. If it were quadratic, we can't possibly build it in linear time. We just need that time to write it out. The trick here is the tries could be big, but the compact trie never is, especially if we store the leaf labels just with an index. The whole thing is linear time, so theta n space. Okay. T is a standard trie of all suffixes of t dollar is not correct because the standard is wrong, but a compact trie is correct with this little, like, use the index in the leaves, not the full string. The leaves store a copy of the entire string. No, we can't do that. That would use too much space. So we just use an index. The naive construction, where you've seen me struggle so much, takes quadratic time in the worst case, but we can do much, much better. T has n leaves. That was a mean one. It's n plus 1 because we have added one more character. But yeah, apart from that, it has one leaf for each of the suffixes.